So I'm going to look at problem 40 from chapter 23. Okay. And this is another problem where you calculate the potential due to a continuous charge distribution. You have a rod, and they put this on the coordinate axis like so. The rod, two sides are of length L, and we are given some charge distribution on this. The linear charge density on the rod is lambda A times x. So this is lambda A times x. And we are to determine the potential for A points along the y-axis and points along the x-axis outside the rod. So points along this axis and points along this axis. So points for the perpendicular bisector of this rod and for points along the rod. Okay. So let's start with this part A, y-axis points. Now, so when you look at this charge density, and if you consider a little part on this rod, what's going to happen is that the charge on this little part is going to get smaller and smaller as you come to the origin, and it's going to get larger and larger as you move away from the origin. It's going to have its maximum value at the end of the road, and as you pass through the origin, it's actually going to change sign. Okay? So on the right hand side, the charge at this little piece is going to be positive. I'm assuming that A is a positive constant, but it doesn't really matter. And on the left hand side, it's going to be negative, right? But in any case, it's going to flip sign. Okay? Even if A is negative, then it's going to be negative on this side and positive on that side. So the main argument actually doesn't change. Do they give if A is positive? Not really, but as I said, the main argument is not going to change. So what you can say is that for every part of the rod that's on one side of this, there's another piece that's going to have exactly the same but opposite charge. Same amount but opposite charge. And so because any point on the y-axis, which happens to be the perpendicular bisector for this rod, is equidistant, by symmetry, the potential of these two are going to cancel each other. Okay? So one is going to contribute dq by 4 pi epsilon naught r, let's say this is r, and the other was going to contribute minus dq 4 pi epsilon naught r. Okay, I mean, add these up, it's just going to be 0. And since we can do this for every point on the right hand side and every point on the left hand side, the sum has to be 0. Okay? But so this is somewhat accidental. How would you do this if there was no cancellation like that? Right? So the idea is, of course, to write this as an integral and then take the integral, and that integral actually come out to be 0. So let's try to do that. Let's try to do this with an integral. So I'm going to, first of all, I'm going to choose something a bit farther. Okay. So I'm going to call this really r. So the potential at this point is going to be the integral of the contributions from each of these little points. Okay. So each of these little points is going to have some charge dq, say dq, and that dq is going to be just our line density times the incremental size of these guys. So it's going to be lambda times dl, and of course it's very convenient to choose this dl to be along our x-axis, so it's going to be dx. So this is going to be ax times dx. And what about this r? Well, this r is going to be, so I'm going to be at some distance, let's say d from the y-axis, and so that r is going to be d squared plus x squared to a half. Okay, I have a right triangle here. This point is of distance x from the center of the rod. This point is of distance d from the center of the rod. So the hypotenuse of this right triangle is given by Pythagorean theorem. Okay, so that dv is going to be dq by 4 pi epsilon naught r, and now I can write what I have. This is going to be ax dx by 4 pi epsilon naught x squared plus d squared per half. And I need to take the integral from x equals minus L to x equals L. Okay? And you take this integral by substitution, right? That's the formal way to do this. So you call x squared u, then this x dx is going to become a half du. And you can proceed that way, but there's another way to look at this. So this is over a symmetric interval. Okay? So over a symmetric interval, we have an odd function. Right? So the denominator here is the same for x and minus x. If I just substitute x for minus x, I get the same thing. For numerator, it flips sign. If I substitute x for minus x, the numerator flips sign, so which means that this whole integrand flips sign for x to minus x transformation, which means that the contribution from the negative values of x is going to be equal to negative of the contributions from the positive values of x. So the total integral is going to be 0. I'm not going to do this, but this is something you can also try and do formally. Okay? So if this was something different, then you would actually need to take the integral. In this case, it's just going to be 0. All right. So for the second part, for part B, we are going to look at a point on the x-axis. Okay? And we proceed in exactly the same way, except we are going to have a different integral. So now I'm going to be at a point, let's say here. And again, I'm going to look at the contribution of these points on the rod. So that point now is going to be of distance d. Okay, so I'm going to calculate the potential at a point d. And the distance between this point that I'm choosing and the point that makes the contribution to the potential is going to be r. So it's going to look like this for points on the x-axis. This is going to be the contribution. So that r is now going to be, so this point's coordinate is x. That's my integration variable. That's going to be d minus x. And otherwise, I proceed exactly the same way. Okay? So this becomes x equals minus L to plus L. dq is still a times x times dx divided by 4 pi epsilon naught d minus x. Okay? Excuse me. And you might be worried that I'm just subtracting this off. So this is going to, does this really ever get larger than d? It does, right? So if I'm on the left-hand side, if I start from minus L until I reach the origin, this is going to be a negative number. This here minus, this x is going to be a negative number. So d minus x is going to be something larger than d. So I'm really integrating, I'm starting from a distance, d plus L, as it should be, right? So this is d, this is L. So I start at d plus L, and I end up at d minus L, okay? As I reach x equals L. So this checks out, and then you need to take this integral, and the way to take that integral is perhaps to call this d minus xu. Then your du, your dx becomes minus du, okay? And then you make a substitution there, and your x becomes d minus u. So that simplifies the denominator, but it complicates the numerator. Okay, so but your numerator, you can actually divide this into two integrals, and one of them is going to have d, or the other one is going to have u. Your denominator is always going to have u, so one of them is going to be a constant, and the other one is going to be 1 over u. And the integral of 1 over u is going to be logarithm. Right? So this integral, when you take it, it's going to produce a logarithm. Don't be surprised. It just happens that for this problem, the potential involves a logarithm. Okay? There's no deep physical reason for this. It's just a mathematical outcome. But when you get the logarithm, do not be surprised. And this is, in fact, how you should proceed to take this integral. Make the substitution and then divide your numerator into two sums. Right? So something like this. So A plus B over C is going to be A over C plus B over C. Okay, so you take two integrals. Both of them easy to do.